Hello all. We are here to present about the GoPro, how GoPro collects data and GoPro's big data platform. The talk has been sponsored by Tableau. And how this talk will be structured is we'll start with what GoPro does, what has been a data journey. Then we'll talk in detail about GoPro's data architecture. David will take you guys through that. And finally, Christian is going to talk about some visualizations and some brief demo to talk about how we use visualizations. We use both Tableau and AWS in a bit different way than others, and we will take you guys through that. In the end, there will be a Q&A, and we will take any questions that you may have. So this is just a brief slide about us and what we do at GoPro. So before we get started about data at GoPro and what has been a background and how the company got started. So when we got at GoPro, GoPro was mainly a camera company, and now we are slowly transitioning to be a software and a platform company. And how data analytics was done, like how was the initial cameras developed, was based a lot on word of mouth. So as soon as somebody will build a new prototype of a camera, we will give to the GoPro athletes. They will go surf with the cameras, try to figure out how people are using the camera, what is working, what is not working, go and iterate. A lot of the data analytics was based on word of mouth and our founder, Nick Woodman. But over the last couple of years, we are slowly transitioning to become a software-driven company, a more data-driven company. And we will talk about all the different products that we have and how we manage the data that is collected by all those products. This is some of the different products that we have right now. A lot of you may not know, but GoPro now has a lot of software products. We have, if you buy a GoPro camera, you basically definitely may have known about the Capture app, which helps you connect to the camera and basically capture photos and see stuff. We also have a couple of editing apps which allow you to create automated videos and automated editing in a minute or so. It's called Quick for Mobile or Quick for Desktop. And finally, we have our VR app also, which allows you to capture and view VR experiences. And definitely what we are known for, our cameras, our spherical units. And as you can see, like this is a truly Internet of Things play. A lot of these apps and a lot of these cameras do connect to the internet. Now the latest Hero 5 camera also uploads your data to the cloud directly, for example. So what we have here is we had a growing data needs. We actually have an Internet of Things play here, and we collect all the data, and it is several billions of events every day. And we'll talk about what are the challenges, and just to allay any concerns, we anonymize all data. We only capture data after we get permission from you. So what are the unique challenges for data at GoPro? And a lot of these things will be covered again when David and Christian cover the different architecture details. So we have a variety of data, as we saw in our last slide, both hardware and software products. And our challenge is to basically mesh the data, basically collect all the data and bring it in one place so that we can understand how our products are doing and how our customers are using them. We have a variety of data ingestion mechanisms, both real-time as well a batch pipeline, and we'll talk about that. And I think the next 2 points are something more important, and people don't really talk about that in the big data space, about complex transformations. It is very important for all of us to bring the data in one place and also aggregate it and structure it and transform it so that it makes sense for our analytics team to analyze the data. And we'll talk a bit about that in the next slide. And as you can see, we have a lot of different products. We all have to bring the data together in one place and blend it in a way that it is available for analytics, and also handle privacy and anonymization according to the different laws which are prevalent in different countries. So how does AWS help us? So we mainly believe, and we'll talk about the different technologies, is like definitely faster lead times. When GoPro is an all AWS environment, we started on AWS, and it definitely helps us procure hardware faster. We can try new technologies months versus days. And also, as you may know, like just like any consumer electronics company, we have peak demands times in Christmas and holidays. So it helps us scale up and scale down also very quickly. And David is going to cover some details there. And we'll talk about how Tableau helps us. Christian is go through some demos about that. These are some of the things that we have noticed in how Tableau helps us become a more data-driven company. It definitely helps us go deep with data. Data insights need to be visual. A lot of our users are business users. They're not very technology-oriented. So Tableau allows us to visually see how people are using the products and figure out patterns and do analysis. The other point which I briefly talked about, data is context. So that is something which at GoPro we have done a lot of. We have a standard event taxonomy across all our products, and we try to transform all the data that comes in according to that uniform event taxonomy so that we can have a common definition and a common understanding of different events and different user flows inside the company. And one extra thing that we do, which is maybe different from other companies, is we use Tableau a lot for data monitoring and data QA also. Because as insights are visual, rather than QA people going and really testing the data out, like whether a certain event is coming through or not, we basically use Tableau to tell us, build charts to see how the data pipelines are working. And David is going to talk about that. And that's it. This is our motto. GoPro is definitely a very cool company to work for if you want to come and work for us. And I will hand it over to David to talk about our data architecture, and we will take questions in the end.
Great. Thank you, Gaurav, for getting us started. I'm going to jump ahead here. I'm not going to try that clicker. I'll really screw things up, I'm sure, if I use that. So Dave Winters, big data architect within the data science and engineering team at GoPro. Just to give you a little bit of my background, I spent actually, 2 decades building backend systems, everything from e-commerce backends to search relevance and ranking engines. And then we're always dealing with data processing, data warehousing. And so that's what I'll be talking about today is about our architecture. So we're going to take a little bit of a deeper technical deep dive here. So we'll go ahead and kind of jump right in here. One of the first things I wanted to mention, if you take a look at our high-level architecture diagram on the screens here, is our data sources. So we have both streaming data sources and batch data sources. It's what people today tend to call Lambda architecture. The formats of the data are wildly different. When you look at that in the upper left-hand corner, that streaming ingestion cluster, that is coming from devices. That's, as Gaurav was referring to, typical IoT data. It's coming from cameras, actual the GoPro cameras and so forth, such as our session here. And it also comes from our drone, Karma, and then also from our software applications. So one of the things that people oftentimes don't realize with GoPro is we're not just a hardware manufacturing company. We actually have a huge, very large software division within it. And we produce a lot of software. And the best part is most of it's consumer facing and it's completely free. So it's actually a good price. So it allows folks to basically take the content off of their cameras. People like myself who don't know anything about video editing, I can write all kinds of Spark streaming jobs to process data in real time, but I can't make a video edit for the life of me. But with a lot of our software, you can. And all of those applications are constantly sending us data. So some of them, they just rapid fire as events, as buttons are clicked and so forth. They're rapid fire, sending us events to an endpoint that we have. And I'll go into a little bit deeper in a minute here, another slide on that. Some of them batch up that data. It can be JSON data. It can be gzipped. It can be batched. It can be just single events. And then when you're dealing with these devices, these have very limited processing power and storage capabilities, obviously. And so we use a proprietary binary format, which makes things very interesting on the ingestion side. And they're very, very sparse events that don't have any state information, which we have to rebuild. So we deal with side. On the batch side, and that's in that lower left-hand corner on your screens there, that is basically third-party data. So that's your ERP data, that's your CRM data, web analytics, social media, all of those which are third-party companies. And so we're at the mercy of them when they provide us data and have to work on their schedule. And generally speaking, most of that data, it's available maybe once a day, sometimes twice a day. There are some of the services that'll give it to you every hour or so. But the cadence is very different for batch-oriented. Whereas on the streaming stuff on the upper left-hand side, that's like anywhere from every 2 seconds to every 5 minutes. It's much quicker. So I just want to kind of talk about data sources there a bit. The next thing I wanted to kind of show you on this diagram is really the evolution of our architecture. And that's where AWS has helped us a ton. You can see like the dotted line where it says original cluster. When we started, it was, I'd say, your typical data lake architecture, which means you're doing, the way I break it down is there's 3 different workloads. You're doing data ingestion, so you've got streaming data sources, you got batch data sources, you want to ingest that data as fast as possible. You're doing ETL, right? Because you got to transform that data into a common format. You want to join together data as much as possible so that the end user queries don't have to do all kinds of joining. You want to flatten things out, you want to summarize them, you want to aggregate them. So we call that ETL. So that's our second function, main function. And then the third one is lifting that data, essentially off a disk, right? Got a big distributed system, and getting it to your analytics applications. In this case, it's mostly Tableau. For folks that are doing ad hoc exploratory stuff, it might be Hue, which is the Hadoop UI. And then for some data scientists, it might be just straight up Python and R code. So those are kind of the 3 workloads. When we began, we had that one cluster, and you can imagine what would happen. Analysts would come in, hey, let's take this 100 billion row table, let's take this other 100 billion row table and do a Cartesian product. Something they shouldn't do, but they didn't. And instantly kills your HDFS, kills your I/O, can even consume CPU, and then your ingestion starts to fall behind. Now you can use Yarn for those that are familiar with Hadoop. You can use Linux C groups and some things like that, and basically govern the I/O resources. But the nice thing with AWS is it's a lot easier just to actually separate those workloads with physical clusters. And so that's what we did. And so when you take a look at this architecture diagram again, you'll see we've got 3 clusters. Upper left-hand side is our streaming ingestion cluster. In the middle, we've got our ETL cluster. And then towards the right there is our secure data mart. And so we do streaming ingestion. We use Spark Streaming. And I'll go a little bit deeper in another slide here and talk about the rationalization of the technology stacks here. But we use Spark Streaming, we use Kafka, which is a distributed pub-sub system. We use HBase to do some on-the-fly aggregation. And then, of course, we have a RESTful endpoint that sits in front of that for all of those streaming events that come in from our IoT devices. On the lower left-hand side, that's our batch induction framework. It is just a good old Java application framework, ingest data directly into our ETL cluster. The ETL cluster, honestly, that's really just good old vanilla, like Hive, uses a MapReduce execution engine. You're talking a cadence there of about the fastest it runs is about once an hour or so. And honestly, a lot of that stuff is more like once every 24 hours. Because again, we're at the mercy of those third-party providers when they make that data available. But at that point, we're bringing together all of the streaming and the batch data sources. We're doing the aggregations, we're doing the joins. And then more importantly, we take the JSON, which we've converted everything to JSON at that point. The stuff that we get before, it can be anything. It can be proprietary binary formats. It can be a very nested JSON format. It can be XML. It can be CSV. We've flattened it all out into nice flat JSON files at that point. And one of the first things we do within the ETL clusters, we actually convert those to a columnar format called Parquet. And we'll take a deeper dive in a minute here into that. And then the secure data mart is where our end users, generally speaking, our lingua franca is SQL. That's what pretty much everybody uses. If you're using Tableau, all of our Tableau analysts are definitely SQL junkies. Same thing with Hue. And if you're writing Python and R code, again, you got to know SQL to pull data out of our platform. So let's start to take a little bit of a deeper dive here. So kind of go down another layer of the onion here. So again, 3 clusters, data ingestion, ETL, data delivery. We're going to start by talking about our data induction cluster here. So architecture here is, again, uses an ELB, Elastic Load Balancer, which is provided by AWS. The magic that it does is basically you can write your RESTful service. We happen to be a Java and Scala shop, so we write Java servlets, have it running in a Tomcat container. You virtualize it as an AMI. You set up an auto-scale group, and Amazon takes care of the rest for you. You give it maybe a minimum number of nodes that you want to start off with, and we have a very cyclical curve to our load during the week, which is sort of, I'd say, a shifted e-commerce curve for those who've worked in the e-commerce business. For us, basically, we start to get heavy load on our systems on the weekends, which makes sense. People are out with their GoPros, maybe they're taking some videos while they're surfing, maybe they're with their kids going skiing. They plug in the computer, plug in this either to a computer or connect it to a mobile device on Friday nights, Saturday nights, Sunday mornings, and it will give us fully anonymized logs. And so we start to see a spike there. AWS will automatically scale up our via the autoscale group, number of Tomcat servers, and then we're good to go. We've got Kafka sitting behind our Tomcat servers. What we use Kafka for is basically we shove all those logs in there as fast as we can. Next slide, we'll talk a little bit deeper about Kafka and some of those things, but in a nutshell, for folks who aren't that familiar with it, it has just amazing write throughput. Take about 3 or 4 commodity nodes, you can get 1 million writes per second, which is pretty insane. Probably about 10 times what you get with a traditional messaging system. Very strong ordering of policy for the messages, which means closer to exactly once processing, so we don't get duplication. Shove those logs directly into Kafka, and then we kind of go through this roundabout of Spark streaming jobs that are pulling logs off of Kafka, maybe doing some flattening of the various events. So they stick them back into Kafka, and then other Spark streaming jobs will pull them off, continue to do processing until we have gotten the actual events nice and flattened out, and we write them to HDFS. And then we have a scheduled job that about every 30 minutes we'll start to copy those to the ETL cluster. So I want to talk a little bit more about basically that interaction between Kafka and Spark there. So you saw that there was kind of that circular pattern, Spark jobs pulling logs off of Kafka, then sticking them back into Kafka. The reason why we do that is basically described here in this diagram. And what we're doing here is we have a reusable set of Spark streaming jobs. At the very kind of root of that tree of Spark jobs, you'll have very generic jobs. It'll do things like we take PII very seriously at GoPro. We're aware of all the international laws and so forth with those things. And so the first thing we do is we take care of all the PII. We remove, we rehash, we do whatever we have to do to make sure that we're in compliant. And so that's a very generic job. All of our logs go through that. As you kind of work your way down that tree of Spark jobs, they'll become more specific. We'll start to basically route the logs based on the type of data they are. If it's a camera log, it'll go into a set of topics for cameras. If it's a mobile log, it'll go to another one, desktop log, and so forth. And then at the very end, kind of those leaf nodes, those last Spark jobs right before those HDFS folders is where we handle what we call the impedance mismatch between Kafka and HDFS. And the challenge there is that Kafka loves small little messages, like 1K messages. HDFS wants like 1 gigabyte files. So you're off by, 6 orders of magnitude there, about 1 million times. And so what we actually do there is that's where we actually queue up the data. We wait until we have enough data and we do a nice big write. HDFS loves that. And then the files are all ready to basically do our ETL processing much faster. So trust me, it gets a little easier there. The real-time streaming stuff is by far our most complicated stuff. Now it actually, as we go from left to right, or our 3 clusters, we're going to move to ETL. It gets a lot simpler. At this point, we have a merge, basically. So we bring in, from the top of this diagram, you'll see the streaming data, bring that into HDFS within our ETL cluster. Then we have our batch induction framework. This is our good old Java application framework, which is just custom to what we wrote. It's got a scheduler that we use. Some of these jobs run once every 12 hours, some once every 24 hours. There's a few that run a little bit faster than that. But they basically have adapters that we've written that know how to pull down extracts from third parties such as Salesforce and Google Analytics and YouTube and NetSuite, and all kinds of different services. They pull those down. It's a wide variety of different data formats, again, JSON, text files, CSV, XML, nested JSON, flatten that all out. So what you end up with, again, is JSON. So the ETL cluster for its input, so this nice flattened JSON, the first thing we do is we convert that to Parquet. So Parquet is a columnar format. It's great, means it's great scan performance, great scan speeds, great for analytical queries. It also means it compresses very well. We flatten out our data a lot, and so what that means is you have a lot of repetitive values. And if you use a compression algorithm, especially something like a gzip, it compresses down insanely well. About 100x is usually what we see. So one of the best ways to improve the performance of a big data platform is proper compression. Because if you use JSON, the data is just enormous. So as soon as we convert it to Parquet, we're ready to basically start to do our joins and our aggregations. So we start doing our joins and aggregations using Hive MapReduce. It's not the speediest thing, but the thing with MapReduce is that it almost always finishes. And so this isn't like super, in a rush data, and so it can run for a little bit. We make sure it's correct. Again, we save it as Parquet files. We add the schema on top of it at this point. So we've taken it from raw JSON, which has no schema assigned to it, and now we've given it an actual schema, and we put that into the Hive metastore. So essentially, we have relational tables at this point. So the next thing is now we're ready to make this data available for the analysts. So we do a distributed copy to what we call our secure data mart. And again, this cluster is actually getting, what happens here is a bit simpler from the previous two clusters. The biggest challenge here is the security part of it. So at GoPro, we're very concerned about security. We want to make sure that people are looking at only the data that they're allowed to look at, that they can't see any other data. So we use something called Apache Sentry, which basically allows you to create access control lists based on Active Directory groups, uses Kerberos for the authentication, and then we lock down all the data, not only at the relational table level, but also at the HDFS level. So even if somebody tried to circumvent and say, oh, I'm smarter than you, I'm just going to circumvent Hive and go straight for HDFS, we still have them locked out. So we make sure that people can only see the data that they're allowed to see. We use Impala, which is our in-memory SQL execution engine. Basically, you can think of it as it's about 100 times faster than using Hive with the MapReduce execution engine. And then the applications that are connecting to it are primarily Tableau for all the viz and dashboards. And Christian will walk us through some pretty cool dashboards that we have. Again, we use the Hue, which is the Hadoop UI for more interactive querying, and then good old-fashioned Python for a lot of folks. So I wanted to talk just a little bit about, making that improvement that we did from kind of our version 1.0 platform to version 2.0, which is where we went from one cluster to 3 clusters, separating data ingestion from ETL, and then from data delivery. The good things are you get isolation workloads, which is great. You get fast ingestion. You get the security with Apache Sentry. You get fast delivery of queries, which is using Impala. They're loosely coupled clusters, which we love, because if you get a new application in-house and they need a different version of Impala, you can upgrade Impala without affecting the data ingestion, so we love that. But there's always areas that you can improve, right? And so this is with the 3.0 architecture that we're currently working on. The things we want to improve, multiple copies of data. If the data was streamed in, we may have up to 3 copies of the data. And it kind of comes back to, well, where's the system of record here? Which data should we believe? Tightly coupled storage and compute, lack of elasticity. We definitely have that challenge today. 3 static clusters. We know we need to double or triple resources during the holiday season. Growing HDFS clusters and shrinking them is a very, very painful task, not something that we look forward to. And then there's just the operational overhead. Multiple clusters that you have to maintain is not fun. So some of this is future architecture. Some of this is actually already in place. So the first thing I would call your attention to is right there in the middle. And you'll see that we have 1 Hive metastore versus we had 3 previously, 1 for each cluster. Today, we're working on having just 1. And then we have 1 Amazon S3 bucket that houses all the data. And what this allows us to do is precisely what you see on the right side of the slide there and on the top there. Suddenly you have ephemeral clusters. It means clusters you start up and you shut down. So instead of getting into the situation where we have a cluster out there, a secure data mart, everything's all set up, and an analyst comes in and they're like, yeah, well, you know something, Dave, we got to take that 150 billion row table, and we got to join it with another 150 billion row table, and we want to do this and that. And you're doing some calculations, you're like, you're going to need 100 nodes for that. That's crazy. Well, we can actually do that now. You spin it up, you run it for a few hours, maybe a few days, and you spin it back down. You don't have to maintain these clusters 24/7, 365. And storing data in the AWS S3 buckets allows us to do that. Same thing for that ETL cluster. Sometimes that ETL cluster is used for several hours, and then it's not used for another 10 hours or so before another job kicks off, you know, in that 12-hour cadence. So why are we paying the bill, basically, for it to sit there for 10 hours? Same thing, storing the data in S3 buckets allows us to do that. And then the other thing, which is more on the software engineering side, which we've done, is taking that batch induction framework. And previously, you saw that it was like writing directly into that ETL cluster. We're actually redirecting that directly into our streaming ingestion cluster. We actually take that data and we shove it into Kafka. What that allows us to do is basically go from 2 code lines to 1 code line. So whenever you reduce the number of lines of code that you have to maintain, high efficiency there. The second part that we're doing there is you'll see that the output from the streaming ingestion cluster is no longer JSON. It's actually Parquet, and it has the DDL. So what it means is we have dynamically defined the schema of that data, and then we've put it into a highly performant format, Parquet, which is highly compressed, 100 times smaller than what we're dealing with the JSON, and we're ready to go. In fact, some of our analysts who are more advanced, and they don't even want to wait around for us to do all this heavy ETL processing, they can hit that data in a more real-time fashion. So with that, I'll hand it over to Christian so he can show us some of his badass Tableau dashboards and vizzes.
Hey everyone, I'm Christian. I'm an analytics engineer at GoPro, and I'm also heavily involved in the administration of Tableau server. So first, I want to briefly go over our Tableau server setup. Compared to a lot of other companies, it's not that big. So we do have about 76 extracts being refreshed throughout the day, and about maybe a fifth of them are in intervals in less than an hour. 120 active users, but we really only see concurrency of about 3 at a time. And our setup is we have one primary machine, and that runs all of the processes except for the backgrounder. And so the worker handles the backgrounder, and what the backgrounder does is basically all it does is it refreshes the extracts in Tableau server. And so we find that for us particularly, I know that at other companies it might be different, but our Tableau server workload is compute intensive, so we go with the C4 instances. So the great thing about having Tableau server on AWS is that you're able to experiment with different sizes, and when we first started out, we found that just having a C4 2x large for the primary was big enough, and a C4 large was good enough for the backgrounder. And so right now, since we have a larger number of extracts refreshing throughout the day, we since then have moved on to C4 8x large for the primary and C4 4x large for a worker. And so I like to put the Tableau visualizations in 3 different categories. So we have our pre-ETL, which is for data discovery, prototyping, and QA. Operations, which is just monitoring the health of the data stream. And analytics, which, all of the dashboards that are created by the analyst teams, which drive insights. So first, I would like to go over operations. So using Tableau for operations allows us to monitor data as it reaches essentially what is the final landing point, the visualization. And so here's an example of a simple operations dashboard. And so you can see here, these are just a count of records, and you can see an anomaly that happened on one particular day. Say, the data might have been fine throughout the whole pipeline right up until this point, and we could use Tableau to identify that. So next is the analytics dashboards. These are all the dashboards that the analysts build. as Gaurav mentioned earlier, our cameras log events. We have the Hero 5, which has a feature we call Camera as a Hub, which can automatically upload your media up to your cloud account. And so first off, since this is essentially IoT data that we're dealing with, it comes in super large amounts. So first off, aggregates are very important for the successful adoption of Tableau. So it's up to analytics engineers such as myself to engage with the analysts to figure out what exactly they want to do with the data, so that we could take these 100 or close to 1 billion events that we receive every day, crunch it down to something more manageable. And so they would use these insights to, for example, with Camera as a Hub, to see, what is the optimal compression for the video that it's uploading, so that we could kind of strike that balance between, good video quality and upload time that the camera performs. Next up is, so we do some real time for analytics, and so an example of that is for user sign up for our cloud service. And so in order to achieve this, we use Hive external tables that read data, that read files straight off of the Spark cluster. And it just reads files right away, right as the files are trickling, and we could see them in a dashboard. Now, it's something like user signups is a great use case for that, because it's a very simple calculation. You're just seeing how many people are getting added to the service. So things like that are great in Spark. And so next off is pre-ETL. So for pre-ETL, I want to look at how we use it for QA, which I find pretty interesting. It's kind of an atypical way to use Tableau, but basically, for example, we have our desktop application, and it logs events, and the developers want to make sure that it's sending events the way they expect them to come in, and so we use Hive external tables for that. And so this is kind of an overview of the process. So you have any flat file. As Dave said, JSON is our file format of choice. So we use JSON Siriday, and we use it to read the files right off of the directory. And so as soon as a QA tester fires off events, they'll be able to see their events come into the dashboard within a few minutes. Right now it's at 2 minutes. So it goes into a Hive external table and then to visualization. And so real quickly, I'll show a demo of a dashboard that they use for QA. And here it is. And so this, as I said, is for QA. So it's really ugly, and thankfully no one's trying to use this to drive insights. So you can see here is we have this tester tracker tab where a tester will go in, fire off some events, and then within minutes they'd be able to see their name pop up here, say like, okay, well, I fired off this many events at this time. This is just kind of for them to confirm that the events went through the pipe. And then they can go and dig deeper into the stats for the particular events. And so they're able to look at this and just quickly, within 2 minutes of firing off the events, see that it comes in, and it comes in, in whatever format is expected. And so I also want to go through how, in the context of Tableau, how we make this possible. So for those of you that don't know, a JSON Siriday is it's just a jar file that you load up into using initial SQL and in Tableau. And it allows you to define the schema. So in this case, it's JSON. And so here, we have this top level key, EP meta, and then this is all of, this is a nested key. And here you see there's a key that's 3 levels deep. And so you just use this to define the schema, and it makes it really easy. And so after you've defined the schema, it's just a typical select query to select each key in the JSON file. And so here it's dot notated. So here you can see it's 2 levels deep here. So you have events exploded dot event. So that's just top level key, events exploded, and then whatever nested key is in there, which is event, and then finally the actual value of that event. And so that is it for my part. Thank you.